There are several possibilities for Pilot Knob, and the context could drastically change the interpretation. 1. Geological context: Texas Hill Country, near Austin. If you're referring to Pilot Knob, Texas, it's the eroded remains of a late Cretaceous volcanic complex located southeast of Austin. In that context, it looks like a low, rounded hill, not a dramatic peak. Is geologically significant as one of the few volcanic features in central Texas, composed mostly of basalt and tuff. Represents a volcanic neck with surrounding sediments of the Edwards and Del Rio formations. May have once affected local aquifer structures, such as the Carrizo Wilcox and the deeper Trinity Group, due to its intrusive nature. 2. Historical or military context: if you mean Pilot Knob in Missouri, it was a strategic Civil War battlefield, especially during the Battle of Fort Davidson 1864. In that context, it's a hill in the St. Francois Mountains of the Ozarks, known for its commanding view of the valley, and was a key defensive position. The knob provided elevation advantage for artillery and troop observation. 3. Symbolic or metaphorical USC: if you're referring to a Pilot Knob in metaphor, it could mean a central control or guidance point, like a literal pilot knob on old radios or machinery. A guiding landmark, similar to how early settlers and Native Americans used isolated hills like Pilot Knob as navigation aids. Could you specify which Pilot Knob you're asking about? Texas, Missouri, etc. Whether you want geological, historical, military, or symbolic context, and what specifically you're trying to understand, e.g., its role, appearance, cultural significance. I'll tailor the explanation accordingly. You said, what does Pilot Knob look like in the context of what I should look out for in the York Creek Valley for undiscovered similar hills of igneous origin within a limestone-dominated region? Chet said, great, you're asking a geological fieldwork style question specific to the York Creek Valley, likely near New Braunfels in Como County, TX. You're wondering how a volcanic feature like Pilot Knob might manifest in that area, and what signs you could use to identify a similar igneous intrusion or remnant hidden within a limestone-dominated karst landscape. Let's break this down precisely. Context. What is Pilot Knob? Pilot Knob, southeast of Austin, is a classic example of a Cretaceous period volcanic feature in the Texas coastal plain. It is an eroded volcanic plug neck composed of basalt and volcanic breccia, tuff, surrounded by marine sediments, especially limestone and marl, a remnant of volcanic activity that intruded into the surrounding Cretaceous limestone roughly 80 to 85 million years ago. Much of it is subdued topographically, not a cone, but a modest hill. Your region, York Creek Valley, Como County. You're in the Volcanoes fault zone, where the Edwards Group limestone dominates, and the area is karstic with springs, caves, and sinkholes. Volcanic features are rare here, but not impossible. What to look for? Clues to hidden igneous hills and limestone. Here are tangible field clues and methods to identify a buried or eroded volcanic feature like Pilot Knob in the York Creek Valley or near by. 1. Topographic anomalies. Look for isolated hills or knobs that break the typical karst plateau morphology. These may resist erosion and stand slightly higher than surrounding terrain. Use LiDAR or 1 to 24,000 topo maps to identify these anomalies. 2. Vegetation contrast. Igneous rock often holds water differently than limestone gives. This may result in thicker vegetation on the volcanic rock due to clay-rich soil from weathered basalt, or bare patches if soil is too thin depending on erosion stage. 3. Soil color and texture. Limestone weathers into white to tan caliche or loam. Volcanic rocks weather into red, orange, or purplish clay high in iron, magnesium. Dig shallow pits in suspect locations and compare soil layers. 4. Magnetism. Metal detector used. Basalt is mildly magnetic. A magnetometer or even sensitive metal detector may pick up anomalous readings. Limestone won't give off a magnetic signal. 5. Rock outcrops. If you find dark, fine-grained rock basalt, andesite, or breccia mixed with limestone. It's a strong candidate for intrusive igneous activity. Breccia rock made of angular fragments with volcanic ash matrix is a major indicator. 6. Hydrological behavior. Volcanic rock often blocks or redirects groundwater in karst systems. If you know of unexpected spring emergence like your 20-foot hole with a flowing stream near your creek, and there's no clear upstream limestone conduit, you may be near an impermeable volcanic structure. This could explain spring diversion from San Marcos Springs if volcanic plugs or dikes disrupt subsurface flow. 7. Geologic maps, magnetic surveys. 1. What might be found at approximately 200 feet depth in the York Creek Valley? Location context. You're near 1050 York Creek Road, which lies just east of the Volcanoes Fault Zone, in a zone dominated by Edwards Group limestone shallow marine karstic, underlain by Del Rio clay, followed by Buda limestone and Georgetown Formation, then deeper into the Trinity Group Cow Creek, Hensel, Glen Rose. At approximately 200 feet depth, you might expect Del Rio clay plastic, impermeable, greenish-gray clay acts as aquiclude, visible in stream banks. Buda limestone dense limestone, often fossiliferous, may have small chert nodules. Georgetown limestone lighter color, thin-bedded transitional zone. Potential anomalies. If present, volcanic plugs or sills would contrast sharply with the above. If you hit basalt, breccia, or red claystone at 200 feet, that would be abnormal and suggest a potential igneous intrusion, especially if it resists drilling, appears fine-grained, or is magnetic. 2. What would a buried volcanic hilly GEA mini pilot knob look like at 200 feet depth? Subsurface signature. A buried volcanic hill or plug would appear in cross-section as a steep-sided column or dome shape extending upward into or through the surrounding limestone layers, likely composed of dense basalt, tuff, or volcanic breccia, possibly surrounded by baked or metamorphosed limestone areole. Detection methods: drilling logs, sudden change from light gray limestone to black or dark green rock with no fossils or fine crystalline texture. Magnetic survey, local magnetic anomalies since basalt is more magnetic than limestone. Resistivity or seismic data. Igneous rock is denser and less porous, showing distinct signatures. Why it matters: implications of igneous rock at 200 feet. Spring flow diversion. Igneous intrusions may block or divert underground flows in the karst system, especially if they intersect faults or fractures. This could explain why your creek shows no surface flow, but you encountered an underground stream 200 feet away from the channel at only 20 feet depth. Mineral or soil variability. Weathered volcanic features can lead to unusual soil chemistry, useful for identifying the spot from the surface. May host trace mineral enrichment, though not likely economic grade. Karst disruption. Intrusions disrupt the bedding and dissolution pathways typical of limestone karst, forming dead zones or redirected aquifers. Summary: what to watch for at or near 200 feet depth. Indicator: what it suggests are colored, fine-grained rock, likely basalt or tuff. Igneous: no fossils in cuttings, none sedimentary rock. Magnetic response: igneous origin, unusual soil, vegetation above altered or non-karst subsurface. Spring flow diversion or underground river fault or volcanic flow barrier. Next step options. Would you like help mapping nearby subsurface walls or geophysical anomalies within a 2-mile radius? Should I show LiDAR, topo plus magnetic overlays centered on your York Creek property? Let me know, and I'll dive in with maps or datasets tailored to 200 feet targets. You said geophysical anomalies, and LiDAR and topomagnetic overlays centered around 1050 York Creek, New Braunfels. Shot said, to investigate potential igneous anomalies near 1050 York Creek Road, New Braunfels TX, we can utilize LiDAR, topographic, and magnetic data. Here's how you can proceed. Accessing LiDAR and topographic data. LiDAR light detection and ranging provides high-resolution elevation data, which is invaluable for identifying subtle topographic features that may indicate underlying geological structures. Texas Geographic Information Office GEO offers LiDAR datasets for various regions in Texas. You can explore their resources here. TXGEO StratMap Elevation Data. Open Data New Braunfels is a local GIS portal that provides access to various geospatial datasets, including elevation models. Visit their site at Open Data New Braunfels. By analyzing these datasets, you can identify anomalies such as isolated hills or knobs that rise above the surrounding terrain, circular or elliptical depressions that may indicate volcanic calders or collapse features, linear features that could represent dikes or faults. Exploring magnetic anomalies. Magnetic surveys can detect variations in the Earth's magnetic field caused by different rock types. Igneous rocks often have distinct magnetic signatures compared to sedimentary rocks. While specific magnetic anomaly maps for the York Creek area may not be readily available online, the U.S. Geological Survey (USGS) provides national-scale magnetic data. You can explore their resources here. USGS Geophysical Data. For more localized studies, consider reaching out to academic institutions or geological consulting firms that may have conducted surveys in the area. Utilizing drone-based surveys. If existing data isn't sufficient, conducting a drone-based LiDAR and magnetic survey can provide detailed insights.